Okay, so kinematics, that was the description of motion. So with this, we had a little bit to it where there were some predictions or some filling in the gaps with motion, but this was before we got into analyzing why the motion was what it was. So this didn't include the Newton's laws stuff, but oftentimes we'll have problems that'll incorporate both. So this thing is moving this way, and tell us this one missing piece of information about how it's moving, and then let's talk about why it's moving that way. Talk about forces or energy or momentum, stuff that goes into that. We had a few different sections to this. We did narratives first off, and on the AP exam, they won't ever give you a question that says, write a narrative description of this, but probably part A or part B of one of the free response is going to be describe the motion of this thing. So that's just a narrative there. Now the level of detail that you go into on that will vary depending on the problem, but we just want to know what types of things to describe. So position, distance, displacement, speed, velocity, acceleration, and how those things change over time, and the right vernacular to use for those things. So, avoiding things like the acceleration speeds up. You sound like a crazy person when you talk like that. The object accelerates or the object speeds up. The acceleration doesn't speed up. That's ridiculous. We have motion diagrams. That one, again, they probably won't have a question like a free response question where you have to make a motion diagram. They are more likely to give you a motion diagram and then ask you about the motion from there. Or maybe they have a multiple choice question or two on there where you have to pick out which motion diagram matches this graph or matches this description or this equation or whatever. Graphs for the next part, position versus time, velocity versus time, and acceleration versus time. Then we had the kinematics equations in 1 dimension, vectors, and then kinematics in 2 dimensions. So for each one of these different parts of the kinematics unit, the things we're describing are position, velocity, and acceleration, how those things change over time. So how position changes, that gets us to things like distance and displacement. Velocity and how it changes over time, that gets us to acceleration. Acceleration will be constant, at least for various time intervals. When it's not constant, the math is too hard for us to do much of anything with it, so we work with constant acceleration time intervals. And that's the next point. Whenever you're describing these things, either in words, in a motion diagram, in a graph, in an equation, we want to break these things up. If there are periods where we have one acceleration and then a period where there's a different acceleration, split it up into 2 different periods of time and work independently on each section. In all of these, we ought to pay attention to significant positions. So, if it's an object is rolling off the counter, then the counter, there's something significant about the counter, and probably it's going to run into the ground. There's significance to that position. When objects stop, so that's a significant velocity. They may give you more information. We're interested in when it gets to this velocity, like a maximum velocity, something there. And when it changes direction, that would go along with a stop generally. Changes direction because it stops and then it starts moving in the opposite direction. All right, for narratives, got an example here. Let me just pick apart. Yeah. Okay, so we can pick apart the different parts of this narrative. Just as an example, car starting from rest. Starting from rest tells us initial velocity is 0. At the top of a hill, that's a position statement. Begins to roll and accelerates downhill. Acceleration there. And direction with acceleration always needs to be included. Acceleration is a vector. Car reaches a speed of 10 miles per hour. Speed there. After 4 seconds, so breaking this up into time periods. After 4 seconds of rolling before reaching a flat spot at the bottom of the hill. It's at the bottom of the hill now. That's a new position. The car then coasts, accelerating opposite the direction of its motion. When something is moving one direction and accelerating the opposite direction, that's another way of saying it's slowing down. Accelerating at 0.5 miles per hour per second, which is goofy English system units for acceleration. We would be using meters per second squared. And travels 140 feet before stopping. So that's another position or how position changes. The 140 feet is. And then stopping, that's a velocity statement there. So the final velocity in this problem is 0. So really a huge amount of information there that we can pull out. And we get lots of practice during class of reading these descriptions of motion and then trying to put numbers into an equation. So practicing with that is definitely going to be helpful. By the by, if you haven't picked up a review book from me, I do have those, plenty of those available. You can check one out today if you like. Okay, as you're writing these, keep in mind that it doesn't have to pass scrutiny from an English teacher, so you may be a little repetitive in what you say with these. So maybe you say that the object is moving forward, and it's slowing down, and it's accelerating backward. Well, the fact that it's slowing down while it's moving forward, you could infer from that that it's accelerating backward. It's okay to be a little redundant there. If you're not sure if they'll know what you mean when you're describing this, then give them as much description as you have to make sure that they will know what you mean. All right, a few places where people get into trouble. The phrases accelerates at and accelerates to. Watch for the units for whatever number comes after this. That'll help out. In fact, as a general rule, know the units for every quantity. There's not a whole lot on here that you can study just by rote memorization, but make yourself some flashcards. Acceleration on one side, units for acceleration on the other. Velocity on one side, units for velocity on the other. And practice with those units. Know that when I see a number in meters per second squared, that's an acceleration. I don't have to think about what that number means because I know by rote that meters per second squared is always going to be acceleration. Accelerates at, that's going to be a statement of the rate of acceleration. So whatever number comes after that is going to be some number of meters per second squared. That'll go in for A in the equations. If something accelerates to, that's going to be followed by a speed or a velocity statement. It accelerates to 60 miles per hour. Well, that's not telling us how rapidly it's accelerating. It's telling us what velocity it ends at. But again, watch for the units where those are present. From rest, or comes to a stop, I guess it's the velocity is 0. Another one that shows up pretty frequently, the idea of an object getting to the highest position that it gets to. So maybe we throw a ball upward and it goes up, slows down, it stops at that highest position, and then it falls. So it has to stop before it can change direction. So when we say something is at its highest position, what we mean is that in the y direction, it has a velocity of 0 for that moment. And probably, a problem like this would ask for or give you information about the position there. So, y equals some number here, and that's its highest position. Not only do we know the y value, we also know the velocity value for the y. All right, motion diagrams. There are all sorts of different levels of detail that these might give. At most, they would give you the positions at different moments in time and arrows to show the direction of velocity and the direction of acceleration. Sometimes they'll get rid of acceleration vectors. Sometimes they'll get rid of acceleration and velocity vectors and just give you the positions at different moments in time. So we just need to be aware of sort of all the rules that go along with motion diagrams. We think of these as being a photo that we took using a strobe light. So a strobe light has a regular pattern of flashes. So every time the light comes on, we see where that object is and get some information. But then when the light's off, we have no idea. No information is given to us between flashes of light. Those flashes of light are equally spaced in time. So that means that if we have two objects that travel, say, a small distance, we see a position here and a position here, and they're a small distance apart from each other, then we could infer that's a small velocity between those two flashes of light. But if we see some other position, some other moment where we have a position here and then a position far away for the next flash of light, well, if it traveled a far distance between those two flashes, it must have been going fast. If it traveled a small distance, it must have been going slow. So even if they don't directly tell us, velocity is this number, show us an arrow and give us a number there, we can infer some information about velocity just by looking at how far apart the positions are. If they do give us those arrows, they may not give us numbers, so we just need to keep in mind that with these drawings and in general, the size of the arrow corresponds to the magnitude of that quantity. So a big arrow for velocity means a a large magnitude velocity. It's fast. Big arrow for acceleration would mean a large magnitude for acceleration. All right, I talked about that a little bit. They might give you just certain pieces of that, so we have to infer some additional information from there. Pretty common to see either an object speeding up or slowing down in one of these. If something's speeding up, the spaces between subsequent positions would be small to begin with. It covers just a small distance between flashes of light. But over time, it covers more and more distance between flashes of light because it's getting faster and faster. So we transition from small spaces between positions to a little bigger spaces, a little bigger, and so on. The opposite is true if it's slowing down. We'd have bigger spaces to begin with because it'd be going faster there, and then it would get smaller and smaller and smaller as it got slower. Graphs of motion, typically we focused on position and velocity versus time. We did have a little bit with acceleration versus time, but those graphs typically are so simplistic that you're not likely to see too much about those graphs on here. Especially since a velocity versus time graph, you can figure out acceleration from that, and it's more work to do that, so they're probably going to make you do the version of this that has more work to it. So the idea was we could transition between these three different graphs, or understanding of these three different quantities, by thinking about either the slope of the graph or the area underneath that curve. So this table just lays out what each of those things mean. Again though, I think the best way to do this is just know the units. If I know the units for velocity are meters per second, and I look at a position versus time graph, I can think, what would the units for slope be, and what would the units for area on this graph be? The one that has meters per second corresponds to velocity. So if I had a graph of position versus time, and I found the slope of that, I'd do rise in meters over run in seconds. That'd be meters per second. So the slope on a position versus time graph has to mean velocity, because the units come out that way. We don't have any meanings for the area under the curve on a position versus time graph. That's just universally not a meaningful quantity for us. There's also no meaning that we have to deal with for the slope of an acceleration versus time graph. That's a quantity called jerk, which is the rate of change of acceleration. But for all of our problems like this, we're going to have constant acceleration. So the jerk would be 0. Ooh, got a new cell phone up here. Oh, it's recording, I see. If you're interested, my students last semester helped me figure out that the rate of change of jerk over time is snap, and the rate of change of that over time is crackle, and then after that it's pop. So, way to go, physicist. A little whimsy in those names. With the area under the curve, we ought to pay attention to the fact that when we go from velocity, area under the curve of a velocity graph, we'll have some distance in meters per second multiplied by some distance in time, some distance in seconds when we do the area there. So that gets us to units of meters. It'd be easy to look at that and say, oh, meters goes with position, but on those graphs it actually corresponds to the change in position. So we don't know where an object is just based on the velocity graph. We can tell how far it goes in a certain amount of time based on that graph, but not where it is. We'd have to have extra information about where it started in order to figure that out. Just like if I told you I'm driving 60 miles per hour, you don't know where I am. Well, I'm right here, and I'm clearly not going 60 miles per hour. But if I called you on the phone, hey, I'm going 60 miles per hour, you'd be so confused if I called you on the phone and just shouted that at you. But you wouldn't know where I was, and probably wouldn't even care. Okay. All right. Let's see, a little more summary here. So we're going to pay attention to the slope, to the area under the curve. We also, on an individual graph, can look at things like the x or y intercept and get some meaning out of those things. Or just where we are relative to the axes. Are we in the positive or the negative region? So on the position versus time graph, excuse me, position versus time graph, this is all the things that we could observe on that graph and their corresponding meanings. So position versus time, on the y-axis we'll have position. So if you have a positive y value, that's a positive position, negative, negative. if we have a slope on this graph, slope represents velocity. So positive slope would be positive velocity, negative slope would be negative velocity. If it's a horizontal line, that's zero slope, that's zero velocity, it's stopped. If that thing crosses the x-axis, if the graph crosses the x-axis, it's really not all that significant typically. That means it crosses whatever position we decided to call the zero position, but that may not really mean anything to us. That's not like a stop or a change in direction. It's just it went past that position that we decided to call zero. Maybe there was some meaning to that position and maybe not. If we have a straight line, straight lines have constant slope. So here slope means velocity, constant slope then means constant velocity. If it's a curve, we have a changing slope, that here would mean a changing velocity, either getting faster or getting slower. Velocity versus time. Velocity goes on the y-axis, so positive y-axis, positive velocity, negative y-axis, negative velocity. The slope represents acceleration, positive slope, positive acceleration, negative acceleration. If the slope is zero, if we have a horizontal line, that's no acceleration, constant velocity. If it crosses the x-axis, that's just where we get to a y value of zero. So the velocity is zero. That is an object that stops and then changes direction. It goes from positive velocity to negative or negative to positive. Since the slope here is acceleration, a straight line with constant slope has constant acceleration. A curve that has changing slope has changing acceleration. And last up, not too much that we're going to look at on the acceleration versus time graphs. Like I said, they're kind of boring, so we don't see too much of them. Really, it's just going to be a question of what our y value is here. So if we have positive y value, that's positive acceleration, negative and negative. If we cross the axis, we go from positive acceleration to negative acceleration. So at that one moment anyway, we'd have zero acceleration. We'd have constant velocity while it's at the x-axis, while it's at an acceleration of zero. Then we get on to the kinematics equations. We've got those three equations. There is a fourth one that, I don't know why they don't give it to you. There's actually several different equations that you can add to this. If you're interested, the fourth equation is, I don't have a great way to write this down. The fourth equation is x equals x naught plus 1/2 times parentheses v naught plus v, end parentheses. The 1/2 v naught plus v, that's just average velocity. It's two different velocities added together divided by 2, average velocity. And then if we multiply that by time, I don't think I had the time in there, 1/2 parentheses v naught plus v, end parentheses, and then times time at the end there. If we multiply that average velocity by time, we get a distance. So starting position plus distance equals ending position. They should have everything set up, though, that you can use these three equations. Sometimes it's just a little faster to use that fourth equation. So, I don't know. It might be worthwhile to know that one. These equations, what? Maybe briefly. It's not on the equation sheet, so we don't spend much time on it. These equations are all derived using calculus, but using the assumption that acceleration is constant. So that idea of picking out periods of time where acceleration is constant, that's super important here. If we don't have constant acceleration, these equations don't work. So like if the ball is falling toward the ground, as long as it's just falling and acceleration is 9.8 meters per second squared downward, these equations work. As soon as it touches the ground, though, acceleration changes, and these equations no longer work over that time period. So we have to cut off our equation at that instant right before it touches the ground. So like a ball that bounces, it falls and then it's in contact with the ground, so it's got a force from the ground and then it's shooting up into the air and it's just got gravity on it again. You know, that is not an equation that we can't solve that using just a single kinematics equation. We got to vectors after that. Primarily we use this for adding vectors together, and really after we learned the general process, we most often just used pieces of it at a time. So like resolving vectors into their x and y components, we've done that a ton with two-dimensional kinematics. Maybe they give us a velocity at some angle, we find the x and y components for that. Maybe they ask us what's the overall velocity of this thing at some moment in time. So we have to make a triangle that has the components in it and find the hypotenuse there. The general procedure, if we have to add two vectors together, is to split them apart into their x and y pieces, then add the x's together to get the total x, add the y's together to get the total y. Then we make a new triangle where we have, the total x makes one leg of the triangle, the total y makes another leg of the triangle, and then the hypotenuse represents the overall vector there. So we can find the length and the angle for that vector. Most often, though, we just did little pieces of that at a time, like in two-dimensional motion. If we do have those quantities that are at some angle, rather than all in the x direction or all in the y direction, start off by resolving those into their x and y pieces. Each one of our kinematics equations we can apply either in the x direction or the y, but we don't want to mix and match information. It won't work out. The only thing that can go across that bridge is time. Time isn't direction dependent. So I can use it with my x information or with my y information. Very frequently on these problems, we'll have to do a calculation on either the x side or the y side to solve for time, and then use that time value on the other side of the equation or on the other side of the information. I think it makes sense to record your information in a list like this one. So we have the positions, initial and final, the velocities, initial and final, and the acceleration for the x direction, and then all those quantities again for the y direction. And then I usually put the time right in the middle, just as a reminder that I can use that for either set of information on these. Okay, almost there, and then we can do some practice with this. Most of the two-dimensional kinematics problems that we did were projectile problems, and that is the only force acting on the object is gravity. So as a result, we have no horizontal forces, which means no horizontal acceleration. Velocity in the horizontal direction is constant. Since we have gravity pulling downward, we're typically doing these problems set on the Earth. So then we'd have acceleration is 9.8 meters per second squared downward as well. In the x direction, with that acceleration being 0, the first and the third equation end up being really boring. So if we look back at the first and the third equation, whoops. There we go. In that first equation, if acceleration is 0, that equation says initial velocity and final velocity are equal to each other. Okay, well, acceleration was 0, so I actually figured that out already. If it's not accelerating, then velocity is constant, but, neat. The third equation gets us to the same thing. If acceleration is 0, that last term drops out completely, so we get the final velocity squared equals the initial velocity squared. And since I already figured out that final velocity equals initial velocity, then, yeah, I got that the squares of those would be equal as well. So the first and third equation, not interesting in the x direction. The second equation, though, that's where the action is. So that last term drops out, but we do still have the initial and final position in there, and the velocity. It says initial velocity, but since velocity is constant, we could use the initial velocity or the final velocity or the average velocity or the velocity at any moment in time during that problem. Now, if we have that situation, you can rearrange that equation, get the x and the x naught on the same side. So you'd have the difference in position, x minus x naught, equals velocity times time. Difference in position is distance, displacement. So it's distance equals velocity times time. If you divide both sides by time, you get distance over time equals velocity. So that equation, I know people generally have that equation memorized already. It's actually on the equation sheet. It's just the special case of the second equation when there's no acceleration. So you're welcome to use that. Just keep in mind that that equation lets you calculate average velocity over that time period. It's not the starting velocity or the ending velocity. It's the average. So if it's changing over time, that may or may not be a useful quantity for us. Okay, and let's see. Some extra information that you can get other than the stuff they're just going to give you numbers for. If we launch something horizontally, that means it's not going vertically to begin with. So the initial y velocity is 0 in those cases. If it's at its highest position, again we talked about this with 1D kinematics, at its highest position means it's not going up anymore, it's about to start going down, but for that one instant, the y velocity is 0. If it's launched at some angle, make sure we find the x and y components. Oftentimes I'll see people try and take, say it's launched at 30 degrees above horizontal and it's traveling at 20 meters per second, people will put 20 meters per second either for the x velocity or the y velocity. It won't be either. You're going to have to find the x and y components of that first. Then you can put that into your table. If something starts and ends at the same height, like a lot of these problems, that position would be the ground. Then we'd have y naught and y equal to the same value. Might as well make them both equal to 0 since we get to choose there. So like a ball kicked from the ground and lands on the ground, that's a pretty common example of a problem like this. Zeros in these problems are good things to see. When we see zeros, that means that terms are dropping out of our equations and the equations are getting easier to work with. So yay for zeros. And I think that's it for this one. So